Hey everybody, welcome back. In this video we're going to look at just part of an old AP Physics exam question. This is from 1998, it was number 3, and so there were some additional things to go with this, but I thought D was a good part of this to examine, just to get a real sense for all the different things we can do with these different forces and how to deal with complex systems where we have multiple objects that are interacting with each other. So the idea on this one is that we have this system with two blocks that are stacked on top of each other, and that bottom block is connected by a rope that goes over a pulley to this other mass that's hanging down. And in part D, it says that we have a big enough mass here that we're pulling really hard, and mass 1 is slipping on mass 2. Now, what does that mean? Well, if you imagine these as the two blocks that we're talking about, they're both going to end up getting pulled to the right, but the one underneath is going to get pulled a little bit faster. And so eventually, if we watch this long enough, the blue block would fall off the red one. So I think the first step we need to go through here then is to figure out what forces are acting on each one of these objects and get a free body diagram going on this to analyze the accelerations of each of these. Since all three of these objects are, since mass 1 and mass 2 are now not moving together, it doesn't make sense to treat those as a system anymore. Now, mass 2 and the capital M here, we could still treat those as a system because those two still move together. And so that might be beneficial to us, or you might find that that's more trouble than it's worth here. In this case, so we've been doing a lot with different systems. Let's just treat these all as separate objects, and we'll figure out the acceleration for each of them. Now, the acceleration for M2 and for capital M will be the same, though. So as far as free body diagrams go, for M1, we've got gravity, always downward. I'll call that Fg1. And the normal force, I'll call that Fn1. And then that mass 1 is being pulled to the right, just not as much as mass 2 is. Mass 1 is being pulled to the right because the bottom of mass 1 and the top of mass 2 are rough surfaces. So we have a kinetic frictional force, and I'll call that kinetic friction 1, going to the right. Now for mass 2, this one is the tricky one. We've got, gravity downward, force of gravity 2. We've got normal force upward, Fn2. We've got a downward force because of mass 1, so that's pushing down, and the amount of force there is Fn1. So the same as the upward force that mass 2 is applying to mass 1. We've got, a force of tension to the right. There we go. We've got friction as a result of the mass 2 rubbing against the table going to the left, trying to oppose that motion, Fkf2. And then we've also got the Newton's third law pair for this force, the frictional force because of mass 1. So that one is going to be Fkf1. Mass 2 has a lot going on in it, for sure. And then the last one are big M, or capital M. Much simpler. We've got tension upward, force of tension upward, and we've got force of gravity, and I'll call that 3, downward. Okay, so I do have some Newton's third law pairs in there. I've got the frictional force between 1 and 2, that's a pair there. I've got the tension force between M2 and big M. And then I've got the normal force between those two blocks that are all Newton's third law pairs here. They all do move separately, so it makes sense that I might end up doing a few different equations for finding acceleration here. I see that my big M, capital M, is only has two forces acting on it, so that might be a nice one to do toward the beginning. I'm probably going to be able to find more with that one than I can with the mess that we have with M2. M1 I also see has actually just one force in the direction of acceleration, and that's that KF1, force of KF1, the kinetic frictional force. So that one actually is going to be my simplest case. Even though there's three forces total, there's only one force in the direction of motion. So that's the one I'm going to start with. So for mass 1 here, I've got my net force in the x direction equal to mass times the acceleration in the x direction. And this is for object 1. My net force here is just going to be that force of kinetic friction on object 1 going to the right. And then that's going to be equal to m1 times the acceleration 1 in the x. Now that force of kinetic friction, I don't know a number for that. We won't know numbers for any of these. But I do know that that's going to be equal to the normal force times the coefficient of kinetic friction. And that normal force, we're talking about normal force 1 equals m1 a1x. And then that normal force, if we go back up to our diagram here, that normal force has to balance out this downward gravitational force. So those two are going to be equal to each other. Otherwise, this thing is shooting up into the sky or falling through the block 2. Neither of those things is likely to be going on, so we can assume that this is the same as Fg1 equals m1 times acceleration 1 in the x. And so then we have, let's see, mu k is equal to, Fg1 is the same as m1 times g, which equals m1 times a1x. We have an m1 in both terms, so I'll divide the whole thing by m1. To find my acceleration now is mu k times g. Okay, so that's the acceleration for that first block. Now for the second block, we've got more forces acting on that one, but the process is going to be much the same. Now, I mentioned earlier that sometimes it makes sense to do systems of equations, sometimes it makes sense to leave them separately as objects. When I look at M2 and big M, I see that those two are going to be moving together, and that in this case, if I don't combine those into a single system, what I think is probably going to happen is I'll end up with an equation over here for the acceleration in the y direction, and acceleration will be unknown, and the tension force is going to be unknown. And then over here, I'm going to have an equation for the acceleration in the x direction, and I'll know that acceleration is the same as it is over here, but I don't know what value that is. And then I'll also have my tension force be an unknown. So I end up, again, with two equations and two unknowns. So I'll have to solve that as a system of equations. Now, that's one option. The other option is to treat M2 and big M as our system. And then the only external forces that we care about there would be Fk1, Fk2, and Fg3 that are trying to advance or stop the movement of this system as a whole. Either way, I think you're going to have about a wash in terms of difficulty. But since we need practice with doing the systems on further thought, I think that it makes a lot of sense to do it this way. So my system then is going to be M1 and M2 together. And I'll just call this direction here forward to the right. And so let's say that for the hanging mass, forward is downward. I'm expecting it to move down, so that's why I'm calling that downward. And then for the mass 2, I want to make sure that forward corresponds. So if mass 1 moves downward, or sorry, if big M moves downward, M2 is going to move to the right. So that means I need to call it to the right forward. Okay, so this one we're going to forward to the right. All right. Now, my free body diagram for M2, I forgot to finish this one, M2 plus M. I'm going to have, well, no tension forces, because that's a force between objects within the system. Trying to move it forward, I've got Fg3, which is equal just to the big M times G. I've got, trying to move it backward, FKF1 and FKF2. Now I have values, or I have a value for FKF1 already, or at least I can figure that that value out here. We have the mass of, I'm looking at this line right here. FKF1 is equal to m1 times acceleration 1 in the x, and I have a value for acceleration 1 in the x there. So I'm just going to make a note here that this is equal to m1 times mu k times g. And then that's a value that I'll put in up here. So let's see, I'm going to have net force is equal to mass times acceleration. I'm looking for acceleration. I've got mg going to the right or in the forward direction. I've got minus fkf1, I'm in the backward direction, and fkf2 in the backward direction as well. And that's going to be equal to m2 plus m times the acceleration. Now go ahead and replace the expression for FKF1, so mg still, minus, down here we found that that expression is the same as m1 times mu k, and here they actually give us that the coefficient of friction we're talking about is mu k1, and I should make a note there, minus FKF2 equals m2 plus m times the acceleration. Now my FKF2 I can get by doing the normal force times our coefficient of friction between the block 2 and the table. And so we actually figured out earlier the normal force, but it's just going to be the same as the gravitational force downward on this thing. So we'll have mg minus m1 mu k1 minus, or whoops, that needs to have a g in there. There we go. Okay. Minus mu k2 times the normal force, which will be the same as m2, m1 plus m2. Times g. All right, and then that's going to be equal to m2 plus big M times a. So now I have the terms that I was looking for, and so I'm just going to divide everything by m2 over or m2 plus m. So then a is going to be equal to, just starting from the left side, mg minus m1 mu k1 g minus mu k2 m1 plus m2 g all over m2 plus m. And that is going to be my acceleration for the second box. There's a lot of algebra there, a lot of variables, but really the process to get there is not significantly different from what we've been doing. We've got three forces. We're adding them together and setting them equal to mass times acceleration. and we were careful about which forces to include, only external forces and only forces in the direction of movement. Really the big change here from most of the problems that we've been doing is the lack of numbers. So you're expected to be able to solve these problems with variables. This one is definitely on the hard end of things like that, but not impossibly hard. You ought to be able to solve this one on an AP exam. Well, thanks for watching, everybody. If you learned something, please go ahead and click like. If you think you'll learn something from future videos, please subscribe. And if you have questions or comments, leave those in the comments section below. Thank you again.